In the first 14 days of March 2026, the established rules of artificial intelligence development completely broke down. The trajectory of simply scaling up computing power hit a wall, and the industry was forced into a sudden structural pivot. Over a 2-week span, context windows expanded past the 1 million token boundary. Open-weight architectures systematically dismantled the performance moat of closed proprietary systems. The era of brute force computational scaling was over. Leading laboratories had hit a plateau in zero-shot logical inference. Zero-shot inference is a model's ability to logically solve a novel, complex problem on its very first attempt, without relying on prior examples. To overcome this limitation, developers rapidly abandoned generalized architectures for highly specialized computational designs. The new baseline for frontier models coalesced around 3 specific capabilities. First, context windows holding millions of tokens. Second, dynamic test time computation. And third, native multimodality, processing text, audio, and video directly within a single neural network, rather than relying on bolted-on adapter modules. Feeding massive neural networks more unstructured internet data no longer yields smarter systems. Advancing artificial intelligence now demands targeted, highly efficient algorithmic engineering. Facing intense pressure from rival laboratories, OpenAI abruptly scrapped the prolonged rollout of GPT 5.3. Instead, on March 5th, they launched GPT 5.4, bringing a 1.05 million token context window that immediately neutralized the memory advantages held by competitors. To tackle complex multi-hour software engineering problems, GPT 5.4 introduced extreme reasoning mode. This allows the system to autonomously allocate massive computational resources to verify its own logic in a recursive loop before returning an answer. This heavy test time compute scaling is reflected in the pro-tier pricing, set at $180 per million output tokens. Anthropic took a distinct approach with Claude Opus 4.6. Rather than relying entirely on brute force computational scaling for long tasks, Anthropic engineered a highly efficient memory management system. Their solution is the server-side context compaction API. When a conversation approaches the maximum token limit, this API automatically generates and compresses rolling semantic summaries of earlier phases. This creates an effectively infinite memory horizon for long-running tasks without crashing the system's memory limits. Opus 4.6 also features adaptive thinking, a mechanism that reads contextual cues in the prompt to autonomously determine exactly how deep its internal reasoning needs to go. Developers no longer have to manually intervene to balance intelligence, latency, and cost for every single API call. Concurrently, Google DeepMind launched Gemini 3.1 Pro. This model abandons auxiliary vision encoders entirely. It is engineered to process interleaved text, code, images, audio, and video natively within a single, unified architecture. Across all 3 major laboratories, the competitive metric is no longer raw parameter count. The new standard is the structural efficiency of how models handle memory and execute dynamic, multi-step reasoning. By early 2026, traditional metrics like the Massive Multitask Language Understanding Benchmark, or MMLU, had reached full saturation. Because models had ingested nearly all public internet data, these benchmarks had degraded from tests of generalized intelligence into tests of mere memorization. The industry migrated to ARC-AGI 2. The abstraction and reasoning corpus is designed to resist brute force computational scaling by requiring models to interpret symbolic meaning and novel visual patterns, testing fluid skill acquisition rather than memorized facts. On the ARC-AGI 2 evaluations, Gemini 3.1 Pro scored 77.1%, ahead of GPT 5.4 at 73.3, and Claude Opus 4.6 at 68.8. Yet these frontier systems all fall short of the 85% human baseline, exposing the limitations of pure pattern matching. Measuring software engineering capability generated even more friction. OpenAI conspicuously declined to report SWE bench scores for GPT 5.4, asserting that the evaluation data was contaminated and no longer reflected true zero-shot coding ability. Instead, OpenAI relies on Terminal Bench 2.0. This metric evaluates an agentic terminal environment, measuring how accurately a model can navigate a dynamic multi-hop workflow, selecting and executing external API calls to achieve a goal without human intervention. The raw code generation capabilities of the top models are now functionally indistinguishable. True operational success depends entirely on the agentic frameworks and software scaffolding built around the model, and modern evaluations must test that surrounding environment. Operating a massive 671 billion parameter mixture of experts model at high precision requires a colossal amount of video RAM. Mixture of experts, or MOE, is an architecture that activates only specific, specialized subnetworks of a model for any given token, saving computation but demanding immense memory to store all the parameters. DeepSeek V4 mitigated this mathematical bottleneck through its tiered n-gram memory hierarchy. Only the highest frequency attention data, roughly 20%, is kept in the ultra-fast GPU memory. The remaining 80% is compressed into retrieval blocks and offloaded to much cheaper system RAM or high-speed storage. DeepSeek coupled this tiered memory with sparse FP8 decoding, a technique that uses lower precision 8-bit math for non-critical routing, while keeping complex reasoning paths in higher precision. This hybrid approach accelerates inference speeds by 1.8 times, making million-token context processing more accessible for open-weight developers. While DeepSeek optimized the sequential transformer, Inception Labs released Mercury 2, introducing a completely divergent topological approach, the diffusion-based large language model. Standard autoregressive models generate text sequentially, left to right. A single probabilistic misstep early in the generation corrupts the entire subsequent output. Mercury 2 discards this constraint, initializing the entire sequence as pure noise, and applying a learned denoising function in parallel across all token positions. By refining the entire sequence matrix simultaneously, hardware utilization reaches maximum efficiency. The result is generation speeds exceeding 1,000 tokens per second. To support real-time voice interactions and highly iterated agentic loops, developers must circumvent the sequential bottleneck of legacy architectures. The physics of computation heavily favor parallel refinement. The initial intent of strict United States export controls on advanced semiconductors was to deny Chinese laboratories access to vast clusters of the fastest AI computing hardware. Deprived of the ability to scale through sheer computational power, Chinese researchers were forced into a constrained engineering environment. They aggressively innovated in memory management, synthetic data utilization, and sparse attention mechanisms. The results of this constraint are undeniable. By March 2026, Chinese open-weight models achieved functional parity with the most advanced proprietary models developed in the West. JEPA AI's GLM-5, a 700 billion parameter architecture, scored a 50 on the Artificial Intelligence Index. This made it the top open-source model globally, sitting a mere 3 points behind Anthropic's Claude Opus 4.6. This creates strategic friction for Western enterprises. Developers are eager to integrate highly capable, virtually free open-weight models, but doing so forces them to navigate complex data sovereignty rules across fragmented compliance regimes, like the Rigid AI Act in the EU. The early narrative that Chinese AI models were merely cost-efficient alternatives has collapsed. These models are structurally competitive at the highest levels of logical reasoning and coding, forcing a global regulatory reckoning. Despite these immense optimizations, a profound schism has divided the AI research community. Turing Award laureate Yann LeCun most prominently formalized the critique that autoregressive text generation is a cognitive dead end, possessing no persistent memory and lacking any grounding in physical reality. Because large language models strictly learn statistical correlations from text, mathematical proofs suggest they are structurally incapable of deterministic cause and effect planning. They do not understand spatial geometry or object permanence, making hallucination an inherent defect of the architecture. In March 2026, this critique received massive market validation. AMI Labs, co-founded by LeCun, closed a record-breaking $1.03 billion seed funding round at a $3.5 billion valuation. Backed by an unprecedented consortium including NVIDIA, Temasek, and Jeff Bezos, AMI Labs explicitly abandoned the large language model paradigm to fund physics-aware architectures. The foundation of their approach is the Joint Embedding Predictive Architecture, or JEPA. Rather than reconstructing missing pixels or predicting the next text token, JEPA systems learn abstract representations of reality directly from raw spatial and sensor data. They model the underlying state of a physical environment, to predict how a scenario will evolve over time. While textual models remain the dominant tool for dialogue, high-stakes industrial and clinical applications increasingly demand this deterministic reasoning. For tasks requiring physical grounding, embodied simulation is emerging as a critical parallel path forward. This shift from observation to active generation is already materializing in structural biology. The field has moved past merely mapping existing biological structures to actively engineering them. Researchers at MIT unveiled BoltzGen, executing a process called inverse design. Inverse design is a methodology where a model is given a desired outcome, like binding to a disease-causing protein, and it works backward to generate an entirely novel amino acid sequence guaranteed to meet that constraint. BoltzGen utilized its all-atom diffusion architecture to achieve nanomolar binding affinities for 66% of entirely novel targets in wet lab validations. It successfully synthesized biological matter without relying on prior known structures. In the physical domain, the industrial sector has deployed autonomous and versatile robotics at scale. These fleets are capable of independent spatial reasoning and dynamic task planning without centralized deterministic scripts. This physical deployment is enabled by pushing low-latency inference to the extreme edge. Hardware platforms like NVIDIA's Vera Rubin architecture provide hardware-level acceleration for multi-step reasoning, allowing data to be processed dynamically on factory floors and even by models operating directly in orbital satellites. These architectural shifts have transitioned AI into an active engineer of biological and physical matter. Based on the structural trajectories of early 2026, the race to expand context windows will soon stabilize near the 2 million token mark. Engineering focus will shift toward retrieval efficiency and driving down memory costs. To meet the intense latency demands of real-time enterprise agents, the industry will see a proliferation of hybrid, diffusion-based decoding architectures capable of parallel refinement. As vast capital flows into world models like JEPA, the industry must develop new benchmarking frameworks. Evaluating an agent's grasp of physical persistence and long-horizon planning will render static, text-based exams irrelevant, requiring dynamic, 3D interactive testing environments. Multinational enterprises integrating structurally competitive open-weight models will face severe regulatory friction. They will need to build modular, configurable governance layers to adapt model behaviors for specific international jurisdictions. The discipline has reached a new stage of maturity. The transition from the text-bound, auto-regressive chatbots of the early decade to the hyper-fast, physically grounded autonomous agents of 2026 is complete. We have solved the technological barriers to delegating complex, multi-stage workflows to artificial intelligence. The primary operational imperative now is seamlessly integrating that deterministic reasoning directly into the physical economy.